Okay, welcome to another moment example. So this example is going to be a two-dimensional example where we have this bracket, this rigid body, this bracket, this metal bracket that's attached to this wall at point A. And we can assume that there's a rigid connection here. So it's maybe welded or just bolted to the wall here. But at the end of the bracket, there is a force that's acting at a angle of 60 degrees above the horizontal here, and that has a value of 450 newtons. And the question is asking, what is the moment about point A? So point A is right here, and the force is acting at point B. So in these types of examples, it's always good to see the problem in several different ways. So in this example, I'm going to solve this problem two ways. The first one is breaking this force into its x and y components, and then using those components to sum the moments that are acting about point A. And the second way is the traditional analytical method using the definition of what a moment is. So if you remember, a moment is the cross product of R cross F. So in the second way, we're going to use this equation, but in the first way, I just want to look at this force, break it up into its components, and then find the moment that way. Okay, so to start off, I guess I can do that somewhere over here where I can say option 1, which is just breaking up that force. So we have this force here, and this force has a value of 450 newtons, and it's acting at an angle of 60 degrees above the x-axis. Okay, the first thing I want to do is I want to take this force and I want to break it up into its y component here and its x component here. Okay, so how do we figure out the x and y components of this 450 Newton force? Well, this right here is the hypotenuse of a right triangle, and the sides are the x component and the y component. So for the value of f of x, that's simply going to be the hypotenuse, which is 450 newtons, times the cosine of that 60-degree angle. And this gives us a value of 225 newton. Now we can do the same thing for the y component. That's also going to be the hypotenuse, but this time it's going to be sine of 60 degrees. And this gives us a value of 389.7 newtons. So awesome. We have the x component, which is acting this way, and then we have the y component, which is acting this way. Now you'll notice that for the x component, the line of action for that force is this right here. So when we calculate moment, remember, we need to take the perpendicular distance from that point to the line of action, which is this value right here. So in this case, it's going to be 0.3 newtons. But for the y component, the line of action is vertical, and the perpendicular distance from A is this line right here, which is 0.4 newtons. So really, each of these two components, the x and the y components, are causing their own separate moment about point A. And so in order to figure out the total moment of point A, we're going to sum the moment that this component causes about point A and this component causes about point A. So down here, the moment about A is going to be, well, let's do the x component first. So this component right here, that has a value of 225 newtons. And the distance, the perpendicular distance between this component and point A is 0.3 meters. So I'm going to multiply this by 0.3 meters. Now, what is the direction of this moment? Well, if the x component is acting this way, you can see that it's going to cause a clockwise moment about point A. And we say that in statics and 2D problems that a clockwise moment is going to be negative. So I can put a negative sign right there. Okay, how about the y component? So the y component is this, and it's going to cause a moment in this direction. So in this case, it's causing a counterclockwise, and counterclockwise is positive. So this is going to be plus 389.7 newtons, and that's just the y component, right? Times the perpendicular distance from this force's line of action, and that is simply 0.4 meters. So this times 0.4 meters. Now, if I do the algebra here, I'm going to get a value of 88.4 Newton meter. Now, because this value is positive, we know that the sum, the moment sum of both of these components, the y and the x component, the moment is also going to act counterclockwise. The net moment is going to act counterclockwise. So this moment right here is positive. And if I want to indicate direction, I can just do something like that. And because I indicated direction, we have to put a little arrow over m of a. Okay, so that was sort of way one. Now, way two, or option two, we're going to solve the same exact problem, but this time we're going to use the definition of a moment. Now, the definition of a moment is simply, well, this is m of a. It's going to be r cross f. So the position vector crossed with the force vector. Now, the position vector, let's focus on figuring out what the position vector is first. The position vector is going to have two components, one in the x and one in the y direction. Now, if we look back at this diagram, our position vector is going to be from the point that we're studying. So this is point A, that's where the moment is going to be induced. That is the tail of that position vector, and the tip goes to where the force is being applied. So in this case, B. So this right here is our position vector. And you can see that this position vector has two components. It has some distance along the x, and then it has some distance along the y. And in this case, those values are given, right? 0.4 and 0.3 meters. So in this case, r is going to be 0.4 meters in the I direction plus 0.3 meters in the j direction. Okay, hopefully that was pretty straightforward. Now, for the force vector F, this is also going to have two components, right? This 450 Newton has a x component and a y component. Well, lucky for us, we already figured out what those components were. Now we just need to plug it into this F equation. So F is really 225 newtons in the I direction, right? That's just the x component. And then for the y component, it's this 389. And this is positive 389.7 newtons in the j direction. Okay, so if we just plug this into our definition right here, what we get is this right here. So we have a cross product between the position vector and the force vector. So we can start doing the cross products now. We can start off with this first term and cross it with this first term, but we know that, well, if we're doing I cross I, that's going to be 0. So that first distribution is simply going to be 0. Now we can do 0.4 meters crossed with the j component, the y component here, and that is going to be plus 0.4 meters times 389.7 newtons. Now, we're doing I cross j. And if you remember from our diagram, I, j, k, if we do I cross j, we get a positive k. So this is just going to be a positive k. Okay, awesome. So then we can move on to the y component here. We'll do this component crossed with this component. So we're going to plus 0.3 meters times 225 newtons. Now, this is j cross I. So we're going to get k, but because we did j cross I, we're going to get a negative k. So what I'm going to do is I'm just going to change this plus sign to a minus sign. And then we can put our k unit vector right here. Okay, awesome. So we got one more to do. We have this crossed with this. Well, j crossed with itself is going to be 0. So that last term is just going to be 0. And if we simplify this and add the, or combine the like terms, so this is a k component, this is a k component, if we just do the algebra here, we get about 88.4 Newton meters in the k direction. And you'll notice that this is a positive value. And that's because this value right here is going to be bigger than this value right here. So this is a good way to check our answer, right? Because over here we said, yeah, it's going to be 88.4 Newton meters in the counterclockwise direction, and counterclockwise is positive. And then we did the actual cross product. it also turned out to be positive. So we can be pretty sure that this is our correct answer. So this is the moment about point A due to this force.